Hi everyone, Dr. P here, and in this lecture video we're going to take a look at solutions, specifically aqueous solutions. Aqueous solutions are solutions where water is the solvent. Now, a solution is made up of two parts, a solvent and a solute. And basically, the solute is dissolved in the solvent. So the solvent is the stuff that there is more of. So if you have a sodium chloride solution, you have a little bit of sodium chloride, relatively speaking, compared to a whole bunch of water. Now, lots of chemistry occurs in water, in an aqueous environment, that is. Biochemistry is a pretty important example. Environmental chemistry, stuff going on just in, in the environment. And it's important then to understand how things interact with water. So let's take a look at water as a solvent. So first of all, let's look at a close-up of a water molecule. And it's kind of this big sort of blobby thing. And we've got this ball, that's the oxygen. And then we've got two smaller ones that are the hydrogens. Now, usually we don't try to draw it like that, but rather we will use the atomic symbol, so O for oxygen and H for hydrogen. And then these guys here are covalent bonds. That is the sticks. And water is a bent molecule where we've got an angle of about 105 degrees between our two hydrogen-hydrogen bonds. And this is a model of water here. So the red is the oxygen, the whites are the hydrogens. And this angle between these bonds is about 105 degrees. All right, so water is a bent molecule, and the OH bond is not a 50-50 shared bond. So we don't have electrons shared equally between our atoms. So a typical ionic bond involves transferring electrons, a typical covalent bond involves sharing them. But not all covalent bonds have 50-50 equal sharing. There's more electron density toward the oxygen. Thus, the oxygen has what we call a partial positive charge. So I can draw that in here with a lowercase Greek delta. So I'm going to have electron density pulled towards the oxygen along both of those bonds. That's what these little arrows indicate. The plus is where the electron density is pulled from, so there's positive at that end. So we could write delta plus and delta plus next to our hydrogens and delta minus next to the oxygen. So what we call this property of a covalent bond that's not equally shared, we call it polarity. We say this bond is polar covalent. And overall, our water molecule is polar. That is, it's got a partially positive side where the hydrogens are, and a partially negative end, which is where the oxygen is. And so what happens when something dissolves is polar water can essentially surround ions and help dissolve them in solution. So we'll say here polarity of H2O helps dissolve ions and polar molecules. So an example could be, let's say we had a sodium ion here, and that's a positive charge. So we're going to have oxygen from our waters lining up next to the sodium, sort of coating the surface here, if you will, with our water molecules. So it's going to look something like this, where we've got our waters that come in and they surround, and it's actually in 3 dimensions. They surround our sodium. So this is the sodium, the silver thing in the middle here, sodium ion, and water surround it. Now the opposite could be true, or is true, for chloride. So we'd have our Cl minus, and we'd have our positive side of the water, the hydrogens, would be closer to the negative chloride. So if this is our chloride here, our waters are going to be kind of arranged in some kind of manner, sort of like that, except we'll have a whole bunch more. And so essentially what we get is these ions are coated with water molecules, and then they look like the rest of the bulk solvent. We call that a hydration shell. So we can then take solid sodium chloride and add it to water, NaCl solid. And then if we treat that with water, liquid water, we get Na plus aqueous plus Cl minus aqueous. And there we go. And like I said before, non-ionic, so covalently bound molecules that they themselves are polar are also soluble. So things like ethanol, sucrose. Solubility of ions will vary, and it depends on both the ion-ion attractive force, so how strong is the force between your positive and negative ions, and then also your ion-water attractive forces. Now, ions floating around in solution give rise to a very important property, and that is one of conductivity. And it brings us into a quick discussion of electrolytes. Sorry about that. Let me get that kind of lined up there. There we go. Now, I did talk about electrolytes in lab, and I did a little bit of lecturing before doing the demo. But I just want to mention that, or go over these again. So we have our solution, which is a mixture of, a homogeneous mixture of one substance, the solute, dissolved in another, the solvent. And in water, electrical conductivity is often an identifying characteristic, and things that conduct electricity are called electrolytes. So a strong electrolyte is a good conductor of electricity. A weak electrolyte is a poor conductor. And then a non-electrolyte is a non-conductor. Now, what makes these solutions conductive? It's ions. So in the case of strong electrolytes, what we have is we have complete ionization or dissociation. And by complete, I do mean 100%. So these are things like soluble salts, strong acids, and strong bases. And a little bit later, I'll talk about the strong acids and bases. Excuse me. Excuse my sneeze there. Realized I wasn't going to be able to hold that sneeze for the remaining 5 minutes or so of lecture here. Poor conductors do not dissociate. Weak electrolytes are poor conductors and they do not dissociate. So relatively little ionization or dissociation. And these are things like weak acids like vinegar, acetic acid, weak bases. So weak acids, weak bases, partially soluble salts. And then lastly, we have non-electrolytes where we have no ionization or dissociation. And these are things like covalent polar compounds, so things like sugar, alcohol, ethanol, that is, etc. Okay. So, let's see here. If there's anything else. I think I just want to end the last couple of minutes with a list of strong acids and bases. The strong acids are HCl, HBr, HI, so hydrochloric, hydrobromic, and hydroiodic acids, as well as sulfuric acid and nitric acid, so H2SO4, HNO3, and perchloric acid, HClO4. In parentheses, I'm going to put HClO3, chloric acid, because it's kind of borderline. So the strong acids are the hydrohalic acid, so a halogen with a hydrogen, except for fluorine. Hydrofluoric acid is weak. So hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, perchloric, and possibly chloric acid. So these are things that you should memorize. Strong bases are sodium hydroxide, potassium hydroxide, I guess lithium hydroxide would be one as well, would be considered a strong base, so I'll add that in here, LiOH, anything that's going to give you a soluble OH ion. magnesium hydroxide, MgOH2. And now I have to remember my solubility rules. And, excuse me, remember my solubility rules. And I think we have barium hydroxide. Those are going to be our strong bases. So notice that what we have here, the acids have the hydrogens, the bases have the OH. And these are for our strong species. Everything else we're really going to consider weak. So things like let's see. You know, I'm going to remove magnesium hydroxide here. I just realized, let's do strontium hydroxide because that's soluble. Magnesium hydroxide is not quite soluble. The thing is, though, if you throw magnesium hydroxide in with a strong acid, you're going to get a reaction. So you'll get a reaction between acids and bases regardless of how strong they are. And we'll talk more about that in a future video. Alright, so those are the strong acids, those are the strong bases, and really mostly we're dealing with sodium hydroxide and potassium hydroxide. And of course we have our solubility guidelines as well, so anything that is soluble, those are going to be strong electrolytes. Insoluble stuff will be non-electrolytes unless it's slightly or partially soluble, and then that'll be a weak electrolyte. Alright, so I think I'm going to end things now. We've been going for about 17 minutes, and I've got more to talk about, so there'll be a second part to the solutions, a second lecture on solutions. So stay tuned for that, and in the meantime, stay safe out there. Bye now.